Okay, this is issue number 42 where we will be creating the camera code. To create the camera, I need two structures beforehand, and I'll put them instead of a collision package. I may change that later, as with all things. We need a Frustum, and we're not going to fill out all the helper code for this. We're just going to do type Frustum struct, and then planes 6 plane. And of course, to have a plane, we need to make a plane. So let's create a new plane.go, and then we'll do package collision type plane struct, and this is going to have a normal, which is going to be a matrix.vec3, and we're going to have a dot, which is going to be a float32. P plane, and we're going to set float value float32 index int, and do a switch on the index, and let me make sure this is right. We're going to have dot set x dot set y dot set z. Otherwise, we're going to do p dot is equal to value. Next, we're going to allow us to convert this plane to an array. So func p plane to array float32, and this is probably where we might use. This might be where we use the type float, but for now we'll just return these, and the dot is going to be the w of that vec4. So next we want to create a toVec4, which is going to be similar. I mean, essentially this is a vec4, but vec4 also can be a float64 technically if we compile it in that way. So we'll have toVec4 algebra matrix dot vec4, and we're just going to return that. Next, we want to be able to create a plane. Usually I make the functions for making things higher up actually. So func plane counterclockwise ABC matrix vec3 plane, and we'll just do it the way that I like to do it. Var p plane e0 is equal to b subtract a, e1 is c subtract a, p dot normal is going to be the cross product between E0 and E1. We don't need to normalize, I don't think. Yeah, we can. We can. I was thinking of C where I do p dot normalize separately, but we can actually just do the normal. Wait, is this normalize or normal? I think it's a normal. Then we can do p dot dot is equal to the matrix dot vec3 dot of p dot normal and a, return p. That'll give us our plane, our counterclockwise plane. Now we'll have a function for finding the closest point on a plane. Func p plane closest point matrix dot vec3 matrix vec3. We'll do it my way. If normalized t is equal to matrix dot vec3 dot point and p dot normal minus p dot dot. But right now we're just going to be doing t is equal to the dot of, let me see, the dot of, I like to put them, that's fine, the dot of normal and point minus the dot product divided by matrix dot vec3 dot p normal, and then we'll return point subtract normal, and then scale t. Next, we need a distance. Oh, I figured it out. So let me make sure that's right. I'm going to add in if normalized return matrix dot vec3 dot p dot normal point minus p dot. I think that's what no, I'm not going to do. I'm going to do return matrix dot vec3 dot p dot normal point minus dot divided by that. Cool. So this is, we just have these flipped. Let's just make these the same. So this here should look same up there. Cool. This one just does the scaling. Func point outside of plane, so we can check if a point is outside of the plane. We're going to say P, A, B, C, D, matrix vec3. We'll do it my way. I need to go through and test these, but we're just kind of setting it up so we can mess around with it later. We have something set up. Sig and P is equal to matrix vec3 dot P dot subtract A, and then we're going to do matrix dot vec3 cross B dot subtract A, C dot subtract A, and then sign D is equal to similarly, except we have D here, we got B, we got C, and that's cross product, and subtract A. Okay. Then we're going to return sign P times signed is less than 0. I guess I don't need a dot 0, just used to doing that. Okay, so now we have our plane. Subtract matrix dot cross E0 and E1 normal. Okay. So now we've got our plane set up. We're going to set up our ray.go. Package collision, and we're going to set up the structure for this. So we're going to say type ray struct origin is going to be matrix dot vec3. Direction is going to be matrix 3. So now we want to get a point along the ray. We can do func r ray point distance flip 32. And we're going to return a matrix vec3. And we're going to take our origin. We're going to add the direction scaled by distance. Simple enough. Func r ray. We're going to do triangle hit. We're going to see if the ray hits a triangle. Ray length float 32 ABC. This is the triangle. Matrix dot vec3 bool. S is going to be equal to boy, I'm going to need a segment now. Segment r dot origin, r dot point, ray length. We're going to return s dot triangle hit ABC because we're going to have a line segment. Separately, we don't really want to check the hit and both when they're essentially going to be the same thing. So I'm going to create a segment.go. Package collision. Now, I'm probably going to come back to segment. There's a lot that I have set up for segment, but I just want to get this working and we'll come back to dealing with it later. So A and B, and rather than, let's see, I guess we'll have one for the ray. So func line segment from ray length float 32 segment. We're going to return the ray origin and a point along the ray, given that length. Okay, we're going to skip all the other functions that I've planned for segment, and we're just going to go down to triangle hit and whatever functions that it depends on. So func L segment, L is for line, segment triangle hit ABC matrix dot vec3. Ooh. We're going to do P is equal to L dot A, Q is equal to L dot B, AB is equal to B subtract A, AC is going to be equal to C subtract A, QP is going to be equal to P subtract Q. And now we're going to do N is equal to the cross product of AB, AC, compute triangle normal, can be pre-calculated or cached if intersecting multiple segments against the same triangle. Okay, we're going to say D is equal to dot product of QP and N. If D is less than 0, return false. I guess we can live without this stuff. Oh, this is basically a to-do. Compute the normal can be pre-calculated or cached if intersecting multiple line segments. Yeah. So we can pre-compute that, so we're going to leave that. Compute the denominator and check its dot product. Return if the segment is parallel or pointing away from it. And then we're going to do AP P subtract A. Yep. T is going to be equal to AP in, or dot product of it. If it's that, we will return. So the notes on this is that ray intersects if and only if T is less than, or if 0 is less than or equal to T. And a segment, that's for array, and a segment intersects if and only if 0 is less than or equal to T, which is less than or equal to 1. So we're just going to be delaying some of the more expensive calculation till after that, or after this. So we're going to get the barycentric coordinate components. E is equal to the cross product of QP and AP. V is equal to the dot product of AC and E. If V is less than 0 or V is greater than D, we're going to return false. And then we're going to set W is equal to the negative dot product of A, B, and E. And we'll say, yep, that's what we're saying. V plus Q, yep, that's right. And then we can just return true here. I'm going to get rid of all these spaces. I don't really need them. This is all one thing. I'm leaving this as a note for the caching stuff. So now we have that as part of the ray. We're going to do two more functions that compose this ray. We're going to do func r ray plane hit. And this is going to return, I like to return the bool second. So does the Go standard. So that's what we're going to do. Okay. Let's say hit is equal to blank vector3 matrix.vec3. Success. Oh, we haven't named it. I'll just say I'll make these named hit and success. And the hit is not a float 32. I don't know why. Oh, this was generated. That's why matrix.vec3. So we're going to initialize these guys. Success is equal to false. D is equal to matrix dot product of the plane normal. We don't need the whole plane. We need the, oh, I guess we do. We need the plane position and the plane normal. And we have the normal and the dot product. So let's just change this to plane position and plane normal matrix dot vec3. So plane normal and the ray direction, yeah. If matrix dot abs, so this is a float, d is less than math dot smallest. I guess I should have like a smallest constant here, matrix dot float smallest, just so that I know what I'm choosing here. So let's go to this here, and we're going to say const float smallest non-zero, and then let's go to the float 64, const float smallest non-zero. There we go. So here I can just say matrix dot float smallest non-zero. We'll return. We'll do diff is equal to the plane position subtracted by the ray origin. Distance is equal to the dot product between the diff and the plane normal divided by d. If the distance is less than 0, we're going to exit. Otherwise, we are going to return r dot point distance and true. And then our last function is going to be a sphere hit. Array sphere hit. Center matrix dot vec3 radius max length and float through to bool. The delta is equal to center dot subtract the origin of the ray. Length is going to be equal to the dot product of this doesn't matter, but I don't know. I like it in this order. If the length is less than 0, or the length is greater than the max length plus the radius, return false. D2 equal to the dot product of the delta delta minus the length squared. Return D2 is less than or equal to radius squared. Okay, so with that, we've got our collision stuff started. We mainly have our Ray and our Frustum. Those are the two we want for the cameras. And we can start on the cameras. So cameras. Sorry, we do, oh, I must have made a cameras folder. Sorry, we do a whole bunch of prep work here. But, you know, we aren't going to get anything done doing one little piece at a time. Okay, so we're going to start with our standard camera, and then we're going to work out our orthographic and our turntable cameras from there. So I'm just going to call this standard camera.go. Type standard camera. I'm just going to add just whole hog all the things I think I need in here, and we'll get rid of some of the stuff that we don't. So we need a view, map 4, we need an eye view, which is the inverse matrix of that view. We need a projection, no, not project, projection, an eye projection. We need the frustum, collision.frustum. We need the position. We need the look at. This makes it easier to point the camera at things. We need the up, which is going to be for the look at. Field of view. We need the near plane. The far, I guess I can call it near plane. The explicit far plane. Pitch. Yaw. Width is also going to be a float. Height. And then we're going to have possibly an is dirty. I don't know. We might come back to the is dirty to denote whether it's busy. Art needs to be cleaned up or not. So let's create our function, func new standard camera. Return a standard camera. Now we may derive or embed this structure into another one. So let's have an initialize function separate. So we'll do C is equal to new standard camera. return C, and we'll do C.initialize, C, position, width, height, and this is a pointer. We don't need to pass C in. So we just need the width, the height, and the position. We'll keep these all as default, those ones that it thought we needed. So the position will be a matrix.vec3. Okay, so now we need our initialize function, and this is where we're going to set up all the defaults here. So c.field of view is going to be equal to 60 in this case. C.near plane, standard, but we're going to make it even smaller. We'll tweak all these defaults later. And now we need the c.position is equal to the position. C.field of view is, we already set the field of view. Yeah. We want the c.view is what I mean. C.view, matrix identity, iView. We don't need to set these because they're about to be set. C.projection is equal to matrix identity. We do c.width is width, c.height is height, c.yaw is equal to -90. This is because of the z-axis being forward on OpenGL and Vulkan here. The pitch, c.up, is going to be equal to matrix.vec3up. And then c.set projection, which is going to be an internal function, width and height, which means we don't need to set the width and height here. It's just going to get passed along. C.update view. Okay. So let's start with the set projection of the width and height. We're going to say width is going to be width, height is going to be height. C.update projection. It's just going to be a helper function to update the projection. So now let's create the update projection func update projection I projection is equal to, we need to actually do the projection function. The projection is going to be c.projection is equal to, or c.projection.perspective. It's a modifying function. We'll do matrix.deg2Rad. Now degrees to radians is not set up to be exported currently because it is taking in a random, or it's taking in a generic, it is a generic function. So we'll fix that in just a second. So we do width divided by height, near plane, far plane. Okay. So let's go to degrees to radians, which is going to be inside of config of the matrix. So you see here we have them set to use just an arbitrary float. We'll just make this follow the package math. So we'll change this to radians to degrees, degrees to radians. And the reason we can't use generics, if you recall, is we're going to be using a scripting language. We can use generics, but we don't want to export generics to the scripting language and use them externally throughout the code just because the scripting language doesn't like them, and it would be hard to create any Go scripting languages that like them based off of existing code. So we're just going to change this to be float to match the package float. Get rid of these. And that'll make this happy over here. So now we need the update view function. Oh, we need to finish off this. So we're going to finish off this by update projection. We're going to set the inverse c.I projection is equal to c.projection. And then we do c invert. Is it invert? Oh, I guess it is. What is inverse? No, we want inverse. Wrong one. Inverse. This is a modifying function. Whoops. As we can see here. So that's why we did it that way. Okay. Now we can go to the update view. Update view. Here we're going to say c.view.lookAt. This is a modifying function as well. Position look at up is correct. Then we can do the inverse view. Inverse, same exact thing. c.update Frustum. And we can make this update Frustum function, which is going to be VP is equal to c.view.multiply c.projection. 4i is equal to 3, I is greater than or equal to 0, I minus minus, and we'll do c.frustum dot planes 0 dot set float value VP I times 4 plus 3 plus VP I times 4 plus 0 and I. 2, 3, 4, 5. Just change these. 1, 2, 3, 4, 5. And then we need to do subtract here, subtract here, subtract here. And we need to change this to 2, 2, 1, 1. Okay, I think that's correct. Let's go up here under initialize and let's create a func C standard pointer standard camera set position. Yeah, just have it do that. Yeah, we need to update the view when we change the position. Now we need to create our various helper functions. So func C standard camera set FOV float 32. We want to set the FOV, update the projection. No, we want to set the update projection. Set projection just changes our width and height, right? Set projection change width and height, and then it calls update. Our width and height aren't changing, so we can just call that. So I'm going to set near plane, set far plane, set. Let's do func C standard camera, and we'll do set width. We don't want to do. Yeah, that's fine. Set the height. Now, sometimes we want to set an entire camera's values rather than setting each one of these individually. We'll have a helper function for set, standard camera set properties, and we'll have FOV, width, height, and let's put near plane by FOV. FOV near plane, far plane, width, height, float 32, and this will just go through and set all of those and then update the projection. Now we'll have the set yaw function. C standard camera set yaw float 32. C.yaw is equal to yaw. Before we do that, we're going to do direction equal to matrix vec3 matrix. We need a. Did we expose the cosine function in here? Let's see, these don't have x, y, and z. They're not members. Did I expose these? Oh, I did. Awesome. So we're going to do cosine degree to radians yaw times cosine of degree to radians pitch. Here we do the pitch, and then yaw pitch, degree to radians. So it should be the last one, sine, cosine. Okay. Now we do direction dot normalize. C dot look at is going to be the position at the direction, and then we'll do the update view. And then we're going to do set pitch. That's going to start with the pitch. We're going to get the direction, same kind of thing. And then we're going to say if c.pitch is greater than 89, set pitch to 89. Else, if it's less than 89, set it to negative 89. Okay, just keeping that in a reasonable range. And we do the direction normalize, set the look at, and update the view. And then, of course, those are independent, so now we can create joined function C standard camera set yaw and pitch. Yaw pitch, which is going to be pretty much both of those combined down into one. So yaw pitch, and let me move these up. Yeah, okay. So we want to do the same thing to the pitch. So we'll just take this, copy it down. But I'm also going to add in the yaw just to wrap it around for 360. Why not? Yaw is equal to negative 360. Else if yaw is less than negative 360. This is just wrapping around so we keep the numbers as like a reasonable value. So let's take this and paste it up here. Okay, do that. Normalize, look at, update. Cool. Now we want a couple of helper functions. C standard camera for getting the forward, right and up, so forward. Return that, and we are going to return matrix.vec3 negative c.iview matrix dot mat for x0 y0, or sorry, y2, and then we're going to do 1 and 2 there. That'll give us that forward. Then we want the right. Let's see if it guesses right. This one's going to be 0 0 1 0 2 0. Okay, and let's get that next one up. That one is going to be 0 1 1 1 2 1. Okay, cool. Now we're going to do a func C standard pointer standard camera set look at position matrix vec3 set the look at update. Okay. Now we're going to do the just have a look at function. C standard camera look at point up matrix vec3, and we're just going to assign those two values and then call update. Then sometimes we want to set the position of the camera and what it's looking at. So we're going to do func C standard camera set position and look at position, look at, okay. And one of the things that we want to say is if we set our position, let's say directly up on the y-axis, looking, or yes, if we match the up center position on the up, and we look straight at it, we're going to wind up with some gimbal lock scenarios. So to do a little messing with that to make sure we don't ruin something, we're just going to say if matrix.approx, the vec3 approximate. Oh, I guess I don't care if it's a vec3 approximate. Do I have an approx function? No. Approx. No, I don't. Guess I can add one in here. We'll do func approx AB float. Let's see, absolute value of float A minus B is less than float smallest non-zero. Okay, so now we can do approx. We're going to do position.z look at.z. Did I spell it right now? Look at.z. If those are approximately the same, we're going to say position matrix.vz plus equals some small number. 3 zeros and a 1 is fine. I think I have a function here. No, that's fine. We're just adding. Okay. Now some fun hit camera casting stuff. So func C standard camera ray cast screen position matrix.vec2 collision.ray. So this is just going to return a ray cast given this camera and a screen point on the camera. So x is equal to 2.0 times the screen position dot x divided by the width minus 1, y is 1 minus 2 times screen position y, c dot height. Yep. Then we're going to normalize, we're going to get the normalized device coordinates. So ray normalized device coordinates, ADC. Yeah. It's equal to matrix.vec3 x, y, and negative 1.0. Doing the negative 1 because, again, OpenGL for negative z. We're going to do a ray clip. Let's make sure this is right. This is going to be x, y, negative 1, positive 1. Okay. Ray I is going to be equal to the ray clip dot multiply matrix 4. And we're going to multiply the c dot I projection because we have the inverse projection on us. So origin is going to equal to matrix dot vec3 ray I dot x divided by the w, y divided by the w, and ray I dot c divided by the w. Origin dot add assign the position. Ray I is equal to matrix vec4 ray I x. Or sorry, yeah, this is ray I dot x, ray I dot y, negative 1 and 0. Okay. The result is going to be ray I dot multiply matrix 4. And we're going to multiply the C view. Ray world. Oh, I hit caps. Ray world matrix vec3 result x, y, and z. Ray world dot normalize. I guess I could just make this ray world is equal to res dot normal. And then return collision dot ray the origin and direction ray world. Oh wait, res is a vec4, that's why. Res dot 2 vec3. Oh, I don't have a 2 vec3. Okay, well, vec4. Oh, as vec3. Ray. Res dot as vec3 dot normal. Okay, there we go. So that will do our raycast from point on the screen. Of course, like with everything, this stuff needs to be tested because I may have typed it out wrong, missed a number here or there. Okay, so now we want to do try to hit a plane, and this is useful for, let's say that you want to click on the screen and then drag and then make the camera move with that click and drag. You want to create an arbitrary plane in front of the camera that you can work with. So that's what I like to have this function for. Standard camera try plane hit screen pause matrix.vec2 plane pause plane normal matrix vec3, we're going to return hit vec3 and success bool. Sorry, AI, I do it my way. So we'll do R is equal to c.raycast, the screen pause. D is going to be equal to matrix.vec3 dot between plane normal and our direction if matrix.abs d is less than matrix.smallest non-zero. Then we want to return hit and false. I guess hit and success. Success should just be false. Okay, the difference is going to be equal to plane pause, subtract r.origin. Distance is going to be equal to matrix.vec3 dot, and we're going to dot the difference in the plane normal divided by d. If the distance is less than 0, we're going to likewise return hit and success. Otherwise, we're going to set the hit, we're going to set hit equal to r.point distance and return hit true. Okay, that gives us our plane hit. And now I want a forward plane hit. This is the one where we want to get the plane directly in front of us. Standard camera forward plane hit. Screen pause vec2. And then we essentially want the same arguments minus the plane normal. The normal is going to be based on the camera's normal. So we'll do that. Okay. And here we want to get the forward. FWD is equal to camera forward hit, OK is equal to C dot triplane hit. And we want to try to plane hit the screen pause, the plane pause, and the forward. And then we'll return hit it OK. Okay, cool. Wait, why isn't this just success? Why don't I just return this? Yeah, I don't need these named returns now. Okay, lastly, we just need a lot of helper methods. I'm just going to put those in real quick. Okay, so we got one for position, width, height, view, projection, century, yaw, pitch, near plane, far plane. Just putting all those getters, if you will, in there. Okay, now that we've set up the standard camera code, we're going to want to use this camera. We can plop one into the host just for now, just to exist. And we can make it so that we can render our triangle using this camera. But before we do that, I'm going to make it so that this standard camera can be either perspective or orthographic, and then we'll have the turntable camera as its own. Maybe that it embeds the structure or something like that. So is orthographic bool. And we're just essentially going to be able to set this. It's just not going to be on. I guess we can set it as part of the new standard camera. We can maybe make a new standard camera orthographic. C dot is orthographic is true. I don't really like passing booleans into functions to swap behavior because you don't really understand what it is half the time when you're just looking at through the code. So here's probably where I'm going to split the initialize so we don't call the set projection update view twice. We'll have something like func. I'm just going to duplicate this. Call this initialize values. And then call this one initialize. Oh, I don't know why I'm deleting that. I can just take all this and move it. So we'll have initialize and initialize values. Like that. And this one doesn't need the width or height. I guess we can set the width or height separately in here, even though it gets set double. It's fine. Well, no, we're going to call initialize both times, so let's get rid of this. Okay, so c.initialize values, position, and then with height here. And we can say initialize values here is orthographic. Whoops. And then we can set c.near plane is equal to -1, and c.look at, we're just going to make it look wherever the forward is for now. Position dot add. The problem is we won't have the forward. Might have to do this. All right, let's just, I think the look at is already set to the forward. Let me see. Projection, view, position. Look at's not even set. C dot look at is equal to matrix dot vec3 forward. Okay. So now when we update the projection, so we call set projection, update projection. So this is going to happen if it's not orthographic. So if it is orthographic, else we are going to do this. If it is, we're going to do C orthographic. I think we called it ortho. I could probably call it orthographic, honestly. And I want to center along where we are, so we'll do C dot width times 0.5, C dot, negative C dot width times 0.5, C dot width times 0.5, negative height, positive height, near plane, far plane. There, that's that. I'm going to change this to orthographic. Cool. And now we want to do the update view. So update view, we're going to do a look at if it is orthographic, else look at. I kind of want the perspective to be first, I think. So we'll say if it's not orthographic, we do that. I don't know. Call me old-fashioned. Okay. I'm going to say iPause is equal to c.position, and then iPause.scale assign -1, c.view.reset, c.view.translate to iPause. We're probably going to make this a little more complicated at some point, but it is what it is for now. And lastly, when we do position, oh boy, it's at the bottom. Position, we probably want, well, we do want to get its internal position, but we also have an orthographic position. I don't know, standard, I'm going to just do this. When we need it, we'll deal with it, an orthographic position, which, because we're offsetting it, we're centering it, we're going to deal with that position separately later. Okay, so we're going to leave this here like this, and now we're going to go set up to use this camera stuff. Okay, there's kind of a few hour gap between what I was just saying and what I'm saying now. So I think where we left off is we wanted to get the camera working for the shader. So first I'm going to go to basic.vert, and I want to add in some global data in here. So I'll say uniform struct global data and global data. Next, we're going to add in a few of the things that we need, a mat for view and a mat for projection. I'll also add in a vec3 camera position in case we need it, and something like a float time. This is general stuff. I probably won't fill out the time right now, but just some basic concepts of that global data. Now we're going to create this same structure instead of Go. So let's copy this. And let's go into the rendering folder and add in, I guess we would just make it a part of the shader. All shaders will have this global data that's accessible. Yeah, we make it its own file, I guess. Global shader data.go. Okay, package, rendering, type, global shader data struct, and oops, what the heck? Oh, it's erasing stuff. So we're essentially going to have this same paradigm. So let's just paste this in here, float32, matrix.mat4, matrix.mat4, and the matrix.vec3. Okay, so that will give us the same exact structure that we have here. Oh, sorry, that we have here. Mat4, mat4, vector3, and float time. So these actually can be publicly accessible. We don't need those to be hidden. So instead of our renderer .gl.go, part of the renderer is going to be that global shader data. Global shader data. And when we prepare the frame, we need to prepare this global shader data. So inside of the renderer.go, we'll have prepare. Is that how you spell prepare? I don't know. We'll just call it ready frame. And when we ready a frame, we need the camera. The camera is the standard camera in this case. So we need the address of the camera. And we need the runtime float32. I think those are the only two things that we needed. Camera. Right, let's see. View, projection, camera, yeah, all those come from the camera, and the time is going to be the runtime. So let's copy this ready frame. And let's just put it somewhere down here. Ready frame, func r render or GL renderer, and here's where we're going to set the global shader data view to the camera view. I think maybe these functions, projection, position, and then the runtime is going to be passed in. Let me make sure. Yeah, returns the view. Okay, so we're going to assign all of the data to for it to be ready for us each frame, which means we'll need to get a camera. We'll just place that in the host for now. Okay, and then as part of our draw phase, we're going to ready up our global data. Now let's remind ourselves of our draw. So here we're doing the draw for this mesh, and we're not generally going to do it this way, but we'll fix that once we get further into the rendering stuff. So let's see if we can put a little stopgap or prepare for what we're going to be doing later. We can just take this into our renderer. I don't want to do this yet, but we should probably set it up. So let's stub this in. This is definitely going to change. It's going to be the draw function. Draw. We'll likely need to take in the host here. Host pointer. Engine host. Okay. Oh, does this cyclic? Okay. Okay, to continue to keep this simple, we're just going to pass in the camera. Cameras.standard camera. Yes, and we'll pass in the runtime. This is definitely going to change. We can probably turn this into some sort of interface that we have the draw data in. All right, let's go back to that main. Let's see, we want to pass in, let's just have it use the program and then call this draw function, which is totally arbitrary. So, let's see, standard camera, we don't need that. Renderer, it's GL renderer, let's pass this in here, func r GL renderer. And typically we'd go through the shaders and then go through the materials in the shader and then go through the meshes that are attached to that material and do all the drawing. And we do the instance elements and all that, but right now all we're doing is, since that's happening instead of the main right now, we're going to use the program and then we're going to call what we want to call here for binding out the global structure data. So here we can say r.set global uniforms, which is just going to be a function that we create. We are going to need the shader that we're dealing with because we got to get the information out of it. So shader. This is getting more and more botched at the moment, but again, this is not the goal is just to make sure cameras work. So we'll pass in the shader here, which means we need this shader up here as well. And then we say the shader ID is equal to shader.renderID.glHandle. And then we can say view location is equal to gl.getUniformLocation. And then we're going to say SID and global data.view, which matches up with our shader here, the global data.view. And of course, we need to create this GL function. So let's go up to GL Node.js func. This guy handle string int 32. Have we been returning int 32s previously? No, not yet. I guess result. Yeah, we're gonna return a result here, I guess. And then we can do, let's see, CGL, get uniform location, void CGL, get uniform location, and return this. Now let's check out this function in glad, glad.h, looking for exactly this function. It returns a GL int, yeah. GL char name, okay. So looking good. Let's regenerate this so it gets happy, although it'll do that when I build. And then we want to return a result, res. Cool. So now let's go back to where we renderer GL. So we want one for the view, projection, the camera position, and the time. Projection location, camera position location, time location. So now we'll say GL uniform matrix IV4FV, view location. This is for passing multiples. And the view here, so this is going to be the pointer to the view here. So the view is a non-pointer, so we want to get the address of this, and we want to say unsafe.pointer. I guess since this is going to be a matrix 4 VF, we can just pass in the address of this and have it cast. So let's just do that. Func, this guy, take in a result count, whether we want to transpose it, and then a value of float pointer, no, value of matrix dot map4 pointer. And since we don't need to pass in the count here, we can just pass in a slice of matrix pointers. Means I'm gonna have to change some of this stuff here. Oh, I guess I didn't need to change the first part of the stuff. Matrices. So that's fine. That's fine. You have float pointer address value matrices 0. Okay, that's fine. Okay. So now we just need to change this. We can get rid of the 1 and pass in an array of matrix dot mat4. An array of pointers too. Well, no, we don't want an array of pointers. I don't know if I want to copy it. Most of the time we're just sending 1. So I think it'd be better just to have 2 functions here, just because this is kind of critical. We're sending tons. We're going to be sending tons of matrices. So rather than sending an array here, I am just going to do 1. And then when we need the array, we will then go to doing that. So this will be the address of a matrix 4, which means we don't need to get this. Okay. Let's keep the performance tight where possible. So we need to do CGL uniform matrix void CGL uniform matrix V. This doesn't return anything that I know of. Let's see, glad.h. Yeah, returns void here. Okay. Cool. So now we just need to do the same thing for these guys, and we need to make these functions. So func, this guy, just going to let it fill it out and correct it. Func, this guy. Camera position, no, dot position. Oh no, it is camera position. What is this complaining about? Pointer to a matrix 3. Oh, let's see what it does. Location is result. Count is int32. Okay, we get rid of the count. Yeah, just those 2. Okay, location, count is 1. And then pointer of the values, yep. And then this one's location and value. Okay, now we need to make these CGL. Void. And void. Okay, so now we have those 2 functions. Okay, now we've set our global uniforms. We can try to call this draw here. Now this will be host.window.renderer.draw, and then we're going to pass in the shader, the camera from the host. This will be the host.runtime. So we need a camera and the runtime function inside the host. Func host runtime. There we go. Guess as a flip32, that's good. And then we need a camera, and we'll just make that a member for now. We can change that later. We'll put it right here under Windows, since Windows got to be changing as well. Standard camera. We'll go there. No, not rendering, cameras. Standard camera. Okay. And then we just need to, yeah, okay. I thought I imported the wrong thing. So now we just need to create that camera. Camera is a new standard camera, and this is going to take in a width. This is the. Do we have the width of the window here? I guess width height position. We're going to make it a matrix.vec3. Oh, this has to be a pointer before I forget. Oh, it is a pointer. Okay, matrix vec3 0 0 and say 1. Now we need these functions. Oh, we don't even have. Oh yeah, we have the width and height here. Func w window width. Can I just one line these? These are all just essentially one lines. And then we want the height. Okay, and these are going to come out as ints, so we need to say float32 width, float32 height. That'll give us this camera. And now back in the basic vert, the GL position is going to have to take in the view and projection, and we're going to just treat this as kind of the model matrix is an identity matrix. So we'll just say model mat4 model is mat4 1, and then we can do vec4 pos. Oh, I guess, yeah, that's fine. And then here, the GL position can become projection or global data projection times view times model times position. And we can even just take this, put it over that, put it over that. Okay. And this model will be replaced with the instance data later. So now let's just compile and see what kind of errors we have, what I forgot, and see how that goes. Okay, got an issue with GL get uniform location. GL get uniform location. Oh, this is returning void, so I think this is GL int. Okay. Okay, we got another one. Cannot use rendering new GL renderer as this type as rendering renderer struct literal. GL renderer does not implement rendering renderer method ready frame as a pointer receiver. Okay, so this is where we have to go into the window and change this to the renderer being a, oh no, this is interface. A new GL renderer needs to return a pointer to GL renderer. Okay, camera is undefined, so host window camera. That should not be host window camera, that should just be host camera. We don't have a window camera. That's silly. Okay, so runtime error, cgo argument, go has go pointer to an unpinned, has go pointer to unpinned go pointer. So this is going to be inside of, this is for sure down here when we have these pointers coming in and we're just passing these dudes through. And this is either we've got to pin it or we've got to copy it, something like that. So we might be able to get away with this by treating this matrices as the array that it is. So we'll get the 0th part of it and get the address of that. And if so, that's another reason why we wanted to use them as an array internally. So no, this is still complaining. Let's make sure it is that instead of just guessing. Oh, it could also be because it is passing it like that. Event shared memory has pointer. Oh, this is coming back to the issue we had where um, when we're using a pointer inside of this guy, it's having a hard time passing this pointer around. Let's see what we're going to do here. Unsafe pointer E0, E being event shared memory. Okay, I was messing around a bit, and what I can do is this event shared memory I can turn into a pointer, and then we can say evt shared mem is new, and just pop that up to basically is under render, and then just pass in this guy here, and that will make the Go pointer happy and not complain about pinning, and I don't really care that that's not a member of the struct. Okay, so now we have this going with absolutely nothing in it. Let's just go back to our basic protection view model. Let's make sure that we didn't break anything else. We're going to remove that multiplication first to get our triangle back. Okay, so now we need to see if we're calling everything correctly. Set global. So set global uniforms is called on draw. And let's make sure that we're getting some actual values back from GL when we do this. Okay, we have the handle ID of 3. So now we're requesting view location. We're getting 1. Projection, 0. That's not good. -1. Camera position. Time location, -1. Okay, we're getting some goof numbers on this. So let's make sure that we spelled things correctly here. Global data dot view, global data dot projection, global data dot camera position. And let's make sure things are playing nicely. So view, we get a view. Projection, let's step into this. We're requesting a name, global data dot projection. Our result is 0 from that same guy. This is 3. This is the named projection. Okay, these may be okay because time is not being used in either as camera position, so those may have just been compiled out. That's why we're getting -1 on those. So let's just see what our view is coming up as when we're wanting to set it. So our view matrix is a bunch of zeros, which is not what we want. Our projection matrix, bunch of zeros. Okay, camera position, bunch of zeros. Time, 0. So we're getting a bunch of zeros on this data, but it's probably because we never called ready frame, honestly. Well done. Let's go to close all this stuff. Okay, let's go to main, and we're going to say, just going to cheese it here, host.window.renderer ready frame. And we're going to pass in the host.camera and the host runtime. Draw. Wait, why are we passing the runtime in here and the camera? We don't need either of these in the draw right now. Probably because we need a ready frame or something. I don't know what I was thinking. Let's go back to draw and let's just pass the shader. Clean up the rest of the stuff later. Get rid of that. Okay, let's see what our view is. Oh, we got a bunch of nans. Awesome. The projection is being cool. Oh, not view. Projection. Come on. Projection. Nope, we got infinite nans in there as well. Camera position. And this is not the right camera position. Let's see if we skip a frame, if we get anything better. Nope. So we need to go into host, new camera. Okay, well, for one, we're not even setting the position here. Which should be a part of initialize values. We're not calling initialize values. What's going on, man? Okay, I didn't call initialize values. I did it on orthographic, but I didn't do it on perspective. Okay, let's skip that one. Let's check out our view now. Okay, now we're getting somewhere. Albeit this looks almost like an identity matrix. Projection. Okay, camera position. That's looking right. Okay. Cool. So now we just got to work out our matrix here for what we're rendering. Okay, so I came in here, set up our global data view times model here, but I changed the projection to identity, an identity matrix, and that got our triangle showing up again. So we'll try to work out the projection first and see what's going on here. So instead of the standard camera, set projection, go into update projection, make sure that we're going into the, oh, right here is orthographic. I swapped these and forgot to put the exclamation point there for the not operation. Oh, I guess I can't run this. I gotta change the shader back first. Put that projection back in there and see what we get. Awesome. We got an upside down triangle. Interesting, interesting. Let me check out what we have instead of the main, just to be sure. Okay, -5. So this is left bottom, right bottom, top, just top middle. So yeah, it's correct. So let's check out our standard camera. And let's see, make sure we got everything set up here right. And then we're probably gonna have to check out this perspective function, make sure the code in it is correct. Let's see, perspective. So I see that I have this Vulkan inverts code. Let's comment that out real quick and see if it's the inversion code. Wait a second. No, it's not going to be that because there's some old C code we don't need. It's not going to be that one. Okay, this looks mostly fine. Okay, so got a runtime error, but not going to look too far into that. So I see that it's recording now. I think it's not supposed to be recording. So essentially what I did was instead of the mat4, I changed this to use this helper function, mat4 x1 y1. And then when I went to it, I realized that it was actually going to this Vulkan one because we didn't have this OpenGL tag, which means everywhere it's being used was using the Vulkan version. So I went through all the build scripts, these 4 build scripts, and added OpenGL to them. Then I went into the project template ones and put OpenGL just for now. We can figure out how we're going to mess with those tags later. And then I went into the launch settings and I added OpenGL to those so that it's working with OpenGL currently, although I'm probably going to set Vulkan to default and have OpenGL as some other build alternative or whatever. So at least we're running now. Like I said, I don't know what this crash is yet, but I'll take a look. It probably has something to do with what we just messed around with. Oh, GLES, non.js, get uniform location. So it's having some issues with this get uniform location. I guess we could just print this out and see what's going on real quick. Print line, program SGL, and see if we're getting some kind of odd value in there. Could also be the CNAME. Just go till it crashes. There it goes. When I clicked, it crashed. So looks like it's probably due to some sort of event causing it to render, OpenGL to render on the wrong thread, something like that. That's very, the stack is very symptomatic of a OpenGL call on a wrong thread. So that's probably something else we'll take a look at. I think this camera one is long enough. So that's it for the camera, and we'll have to see. I'll go through the change list and see what possibly could be angering the runtime. So we got a new renderer. Yep, this is all fine. Create window context. Yep. Added some helper functions. This guy's doing nothing but adding interface functions. This one's returning a pointer to GL renderer. When we ready the frame, this ready frame is happening in the main. Then we set globals, which is also happening in the main, and then we draw. Set globals is happening from the draw. It's a global data table, making radians and degrees publicly accessible, changing that to orthographic, getting rid of those comments, using the proper conversion method, degree to rads. So these are probably going to be a lot of degree to rads in here. This added a bunch of C calls here and their wrapper functions. Created a camera, got the runtime, created global data, calling it a main using the projection view from the camera. Segment. It's just math code, math code, math code, Frustum, math code. This is the standard camera, and then a bunch of build scripts and launch, and then main, which just calls ready frame and draw before it does all this other stuff. Standard camera is just a bunch of camera code. So I guess just real quick before we finish this, we'll go to host, and we'll make the camera up on the Y, and the look at should stay forward. That's just how the camera is. The look at is default to the forward of the camera, or the forward of the world. So you'll see that move down. And then if we change this to host.camera look at is the 000, and the up, I guess we have set look at, right? Set look, yeah. Set look at to 000. We should be up looking down. Oh, it's kind of hard to tell. Let's go much higher up. Let's say 10. So it's hard to tell because it's a flat shape. Yeah, now we're up here looking down at it. So our camera is working. I'm just going to leave it like that for the commit. Cool. I'll work out that crash, I guess, on a separate one just figure out what's going on.